Hello, I'm your host, Monique Anderson from Saratech. We are fortunate to have David Garola and Ashley Eckhoff here with us today to talk about design for additive manufacturing using Siemens and HP technologies. Next slide, David. All right, today's agenda is going to cover the key considerations for design for additive, Siemens NX additive software capabilities, design for additive manufacturing for HP MultiJet Fusion, and then followed by a Q&A. But first, before we get started today, I want to just give you a little background on Saratech. For over 15 years, we've been helping customers optimize their design analysis and manufacturing processes. Saratech is an award-winning solutions provider in the PLM space. We have the honor of being Siemens and HP's #1 partner in the Americas. Headquartered in Orange County, California, our team of professionals are located all over the United States to best support our customers. Next slide, David. And to all our attendees, please enter all your comments and questions in the chat box on the right of the screen, and we'll respond to them at the end of the webcast today. And also, if you could just stick around for about 15 seconds afterward to fill out our survey, we really appreciate your feedback. And I'd now like to hand the reins over to David. Thank you.
Thank you, Monique. Thank you very much, everybody, for joining us today. I wanted to start today's conversation with a couple high-level food for thought bullet points, and ultimately why a lot of times people are struggling with or not realizing a lot of the core benefits of additive manufacturing. So I've separated these thoughts out into 3 categories that we see the most use of additive manufacturing: prototypes, tooling, and production. And I'm not going to go through all of them specifically, but a couple to point out, in particular from the standpoint of, say, for example, prototypes. Prototypes might not have as many requirements on the technology. You might be just printing a form fit or maybe limited function part from a prototyping perspective. But when you get into that level, then there's a tremendous amount of options out there to choose from, which can really make it difficult on the customer to make sure that they're getting the right part still. Are they going to get a part that's going to be stable over multiple months under sunlight, or things like that? And then when you move on to tooling, some of the key areas that we typically see is, as you start getting into more cost-sensitive areas, is the cost comparison versus other tooling methods. And we're going to be going over a couple areas that can help you try to sort through or determine what might fit and what might not fit within the tooling arena. And then the last area of production is really the optimization of performance based on the additive capabilities that are out there. And that's where we're going to really be talking and getting into a lot of details about design for additive techniques and considerations. So as we go through and sort through all that vast array of different technologies, it seems these days a new machine is coming out every week that I see on LinkedIn or social media or whatnot. I always come back and advise our customers to come back to this fundamental. So ASTM, the association ASTM, created the 7 modalities of additive manufacturing, and these are those modalities. When you look at any additive technology out there right now, they can always fit within one of these modalities. I'm sure if there's some new technology that doesn't, ASTM will consider it and potentially add another modality out there. Today in particular with HP, we're going to be focusing on powder bed fusion, but we also consider that from our overall portfolio that Saratech offers. And so as you can see here, we offer a wide array of technologies to make sure that we can fit a customer's needs versus trying to shoehorn an application into a particular technology. So that's a big piece of our ecosystem, is making sure that we have a wide array of choices. And as you can see in the bullet points, these are some of the core benefits of those technologies to consider when looking at, potentially either one, getting parts off of these technologies, or two, looking at purchasing a machine yourself. When it comes to our overall workflow of products that we offer, one of the key areas that we focus on is automation. And a lot of people consider automation from the standpoint of just the hardware, robotics, that type of thing. So we do focus on that, but I also wanted to emphasize that we consider automation from the software and also the engineering perspective. So as Ashley is going to be going over here in a few, when you look at the operations that are having to be done manually in a lot of additive environments and the solutions that Siemens provides, it is a form of automation from the standpoint of less operator involvement, fewer steps involved in the entire process, things like that. So we do consider this a core basis of our additive ecosystem, is the automation of these technologies and the integration of both hardware, software, and overall implementation in an environment, whether it be prototyping or production. So one of those actual hardware pieces of automation is that we do work with Universal Robots and post-process. Universal Robots is a cobot type machine that allows for integration of automation techniques. You can do different end effectors on these robots to do different activities. They're very robust and versatile, is what we're looking for, where you can adapt them to different applications very easily. Cobot, meaning they can operate in an environment with individuals surrounding them. You don't have to have safety cages. They have force feedback where they can, if they bump into someone, they can notice that and stop, things like that. And then post-process is another form of hardware automation that we are using to really do a lot of the post-finishing of parts, removal of layer lines, removal of support material, removal of powder in powder-based technologies. So a lot of those steps that typically are done manually and really are a barrier to the ramp up and scalability of use of additive in production, both of these tools can help with tremendously. Then on our engineering services side, we have a full team of engineers. It actually makes up the majority of our individuals at Saratech. We have a lot of capabilities that can range from just doing general design work to full analysis to also PLM and integration projects that are much bigger in scope across an entire corporation. So those are things to consider when wanting to implement a new technology such as additive and how that might affect your entire workflow of files and processing of designs, things like that. So just a consideration. And then just briefly touching on the software, because Ashley is going to talk much more about this. Wanted to go over that we are a primarily Siemens provider, but we also provide a lot of additive specific softwares such as Magix, which is integrated with Siemens products, but comes into the entire ecosystem as well. So Ashley, I'll go ahead and hand it over to you.
Great, thank you, David. So one thing David didn't mention is that they've got a really nice, well, I guess you call it a boot camp coming up, and I'm sure he'll give you some more information about that here in a bit. But I thought it worth starting out my portion of the presentation by talking a little bit about what Siemens is doing in the area of additive manufacturing and software in particular. Because hopefully if you attend Saratech's boot camp, you'll get to see that in action, play with the various different pieces of software we have available in the context of additive. So if you would move to the next slide, David. So at Siemens, we don't just make software for additive manufacturing. We also have portions of our business, the wider Siemens business, that do print parts every day as part of their daily work in a industrial fashion. So we've got several different divisions of Siemens in the power generation and the mobility areas that print parts like the turbine blade you see here, which actually has won several awards for additive design over the past probably 2 years. We've got another part of our company that makes burner heads, and they've got a really interesting solution where they take a burner head that's corroded from use, and they machine off the top of the burner head. They put it in a special additive manufacturing machine and print a new head on top of that burner, which saves them a great amount of time in getting those parts back into service out in the field. And then we've got our mobility division, which prints some parts for various different mobility solutions, urban mobility solutions like commuter trains and things like that, where those different customers that they have different needs and might require custom parts, for example. So the armrest you see here was a custom solution that was printed for a particular application for one of their customers. So we don't just make software at Siemens for additive manufacturing. We're actually printing parts as part of our daily business, and we try to take the knowledge we get from printing those parts and bring that knowledge back into our software so that all of our customers can learn from the things that Siemens is doing on a daily basis. So as we talk to various different customers out in the field, we see that they kind of go through this journey, if you will, with additive manufacturing. They usually begin by thinking about the different parts they make, the products they make, and how those might be adjusted or redesigned to take advantage of some of the great features that additive manufacturing brings to the table. And this is where we see people think about, reducing weight, reducing the amount of material they have, maybe scanning an old part that they don't have, the CAD files for anymore, taking that part and then printing it, things like that. We see customers kind of starting to begin their journey with thoughts like that. And as they get a little more experience and a little more understanding of how additive manufacturing works, they usually begin to migrate into other areas like reinventing their manufacturing, thinking about, okay, I've got all these parts that are cast, but that's a really expensive and long lead process. Can I take some of those parts and can I print them instead? And if I print them, do I need to redesign them? Do I need, can I get more efficiencies out of them by that? So they kind of start mixing these things together. And when they've thought about reimagining their products and they've thought about how they can reinvent their manufacturing, then they can kind of move to the very next level, which is rethinking how they do their business. Additive manufacturing brings about things like zero inventory. Can I print this close to the point where I need it to be, so that I don't have to have a whole warehouse of parts sitting there that I have to pay for? I can design anywhere, print anywhere. I can do individualization. Lot sizes of 1 become more cost effective. So these are the types of things that we see customers doing as they go through this journey when they start thinking about additive and how it might affect their designs, their manufacturing, and their business itself. So we do see when customers start this process, though, that there are some barriers to adopting this in what we would consider to be an industrial way. And one of the main barriers we see in the market is this disjointed software process. We've talked to customer after customer who has, 4 or 5, sometimes more different individual software solutions that they have to use to get through their additive manufacturing process. So they may have a CAD system that does some simulation, but then if they want to simulate the print, the actual print itself, that's a different package. If they want to prepare the print, make support structures for certain types of printers, or pack parts into the build tray, that's another piece of software. If they want to do topology optimization or lattice structures as part of their design, often that's another piece of software. So you can see easily how you can have this sort of software package creep, where you start out with a nice CAD system, but by the time you're done with additive manufacturing, you've added on several other design systems, maybe a simulation system, a setup system, and you've got 5 different software packages you're using by the end. And so we see this as a real problem. It creates inefficiencies and introduces error into what should be a nice streamlined process going from design down to print. So at Siemens, we've worked hard to get rid of some of those limitations. We've integrated a lot of the major pieces of software that we think you need to do your additive manufacturing job into our NX system. So we have the original design stuff, right? You can design parts in NX just like you can with any other parametric CAD system. But we've also introduced facilities for generative design and topology optimization. And I'll talk about those here in a minute in a little more detail. In fact, I'll talk about the top part of this picture, pretty much all of that in more detail here in a minute. But we also have lightweighting, so lattice structures have been integrated. We have a really awesome system called convergent modeling for adapting those designs as the needs change. And then we've got integrated systems for validation, preparing for printing, doing all the hatching, slicing, and actual export to the printers themselves. And we've always had post-processing inspection CAM systems for removing support structures and stuff like that. Those are, of course, pieces of our traditional software that have been there for quite a while. But you put all of these things together and you get a nice integrated solution from one end to the other that allows you to complete the majority, if not all, of the various different steps of additive manufacturing in this process. And what that allows you to do is it allows you to have some nice data tracking between the various different steps of the process. And I'll talk about that a little bit more when we get towards the end. Maybe we'll discuss that. But for the moment, let's concentrate on the design side of things, since that's our subject here for today, and talk about a couple of these things along the top of this picture in more detail. So I talked about topology optimization. So for those of you that aren't familiar with topology optimization, the way this works is you basically hand the system a bunch of inputs. So you give it a design volume or design space that it can create a part inside of. You give it some keep in areas, some keep out areas. You give it some loads, so it can use CAE under the hood, and you tell it what the material is you want to build the final part out of. Once you've given the system all of these various different inputs, the system then goes and tries to make an optimal part according to the inputs you've given it. So it's going to make a part out of the material you told it to use within the volume you gave it, using the loads that you've given it, and try to come up with a part that uses as little material as possible to conform to those various different inputs. So the way this works is I always describe this kind of like Michelangelo. You know, he starts with a big block of marble and chips away at it and throws pieces away to get to this beautiful statue that's inside the marble, right? So this is kind of the same thing, except for instead of a chisel and hammer, we're using CAE under the hood. And we're throwing away little bits of material that we don't need in order to get an optimal part that conforms to the inputs you've given. So it's a really strong way to design parts, and the reason it's closely associated with additive manufacturing is because depending on the inputs you've given the system, you often end up with parts that would be very hard to manufacture using other methods. So parts like this one would be very hard to machine, for example, using the surfaces we've got here. Now, what's interesting about our topology optimization tool is that it is integrated into NX, so it allows you to do these things and use these parts directly inside the system without having to bring those in and redesign to get parametrics and things like that. So it saves you a ton of rework having an integrated system that does this sort of design. Next slide. So we also have lattice structures. These are something that people use for lightweighting parts. We've seen them used by people like our power division for managing gas flow through certain channels and things like that. We've also seen them used as filters in certain use cases. So they have a lot of different uses, but the main use is mostly around lightweighting a part while maintaining the structural integrity. So there are various different types of lattice structures. We support these three at the moment inside of our system, but again, tightly integrated and allowing you to do this inside of our CAD package so that you never have to do translations and leave and those sorts of things. So the one thing you notice about these systems if you start to use them is that both topology optimization and lattice structures create geometry that is not parametric CAD geometry like you normally have inside of a CAD system. Normally what you get out of those types of tools is a mesh body or facet body. And most CAD systems do not work very well with those bodies. So you'll see people doing this wonderful topology optimization. They'll bring that in from their external topology optimization system, bring it back into their CAD package, and then they'll use the normal modeling operations from the CAD package to totally redesign that part that they just spent hours maybe creating with CAE. And so in our system, you don't have to do that. You can use that geometry directly and then use CAD operations on top of that geometry to modify it as you need to. So for example, if you have a topology optimized part like we saw earlier, you can make the hole smaller with the topology optimization and then go back and put an exact hole with a diameter in that part using normal CAD modeling operations. And that gives you a diameter that has parameters behind it that you can then change if something needs to be changed, right? So you kind of see that progression here in these pictures. We've got an original mesh body. We've subtracted that little cone diffuser at the end of that using a normal cylinder and a subtract. So just an extrude cylinder and subtract. We've added some new CAD geometry. So that's exact CAD geometry, BREP geometry, into that part and united the two together. So now we have at the end a solid that has a new cone with some vanes on it to help the airflow, but it's part CAD geometry and part mesh geometry, and they work seamlessly together, and that part can now be sent out to a printer. So another thing we've done, we kind of came to the conclusion very early on that people needed help understanding what was going to print properly, what parts might print properly, where they might have errors, things they needed to look for when they're printing a part. So we saw that a lot of various different packages existed on the market and had these little checks in them, but the problem was almost all of those packages were doing these checks at manufacturing time. And that's way too late in the process to be finding errors and correcting them, because it's much, much more expensive once you're down on the shop floor to find an error than it is to find it back during the design cycle. So we integrated a series of checks specifically for additive manufacturing into our NX package to allow you to check your part as you're designing it for areas where you may have issues. So this shows a couple of the checks. We've got a minimum wall thickness and minimum radii checks, and every printer, no matter what kind of printer it is going to have a minimum threshold for features it can accurately reproduce. And so you can put in those values here, the minimum wall thickness that your printer can handle, and check for those during design. So again, you're able to find these things as you're designing the part and make those modifications during the design cycle, which is much, much cheaper and more cost effective and time effective than doing that during the manufacturing process. On the next slide, we also have another validation. If you'll switch the slide in, thanks. That one thing that's important for the HP printers that we're talking about here is that they're a powder-based system. So you want to be able to make sure that you're able to extract the powder from around your part whenever you extract the part itself from the printer. And so one thing that we have inside of our system is a checker that will go through and look for areas of the part that have wholly enclosed volumes where you're liable to have trapped powder. Trapped powder can it can affect the center of mass of your part, the weight of your part, the characteristics that you've carefully designed your part to have. If you have trapped powder inside of void areas in your part, then that can cause major problems. So this test goes through and looks for those. And I think it's worth noting that as time has gone on, some of the service bureaus that people send their parts to have started to integrate these checks as well. And what I've noticed is, well, number one, those are again at manufacture time, right? So you've already designed what you think is the perfect part, you're going to manufacture it, and then you finally get some feedback. If you don't have checkers in your software, then maybe that's the best solution you have. But I will warn you about this. Some of the checkers I've seen using service bureaus myself, I think are overly restrictive. I've had parts that I know will print perfectly where a service bureau has given me a warning and said, you have to check a box saying that you're okay with this because we think this part has issues. But yet I've printed the part before. I know it will print just fine. So I think a lot of the checks you see in the service bureau software are overly restrictive, and it's mostly probably just to cover their own rear ends. But I think that having these things integrated into the software you use on a daily basis to design is is a much better situation, because then you have control not only over when those checks are made during the design process, but also the parameters that go into those checks, and you can use your empirical knowledge about what works and what doesn't to adjust those parameters. And lastly, we're not really talking about manufacturing today. This is a design webinar, but I would like to mention real fast that we do have all the various different solutions you'll need for the HP printer and others to set up your build tray, do things like the 3D part nesting you see here to get the best efficiencies you can out of your printer. So if you're a company that owns an HP printer or another type of printer, you can do all of that setup inside of our software and gain these efficiencies. And the really nice thing about having the build tray setup is that for things like support structures, if you have a system that uses support structures, having that integrated system means that if the part changes, we can automatically go down and adjust the support structures accordingly. So it gives us this nice associativity, like I said earlier, between the various different steps of the process, and allows you to easily adjust the process without having to retranslate data and totally redo parts of the solution.
Thanks, Ashley. And so I wanted to, before we just jump on to our next topic, kind of summarize a couple of the key points that we just discussed. We do have much more presentation here, so please don't leave us yet. But really, I wanted to point out one aspect that is probably overused in the industry is, as you consider a lot of this flexibility and design benefits that come out of the solutions that Ashley just brought up, is a lot of people in the industry say that additive enables design complexity to come for free, right? Well, in the end, it really doesn't, in my mind. There are still considerations that you have to factor when you are doing design for additive and or considering additive as your production method. So you need to understand what technology you're using. There are major differences in those 7 modalities that we described at the beginning of the presentation. And then you need to understand what your software capabilities are. As Ashley touched on very well here, there is that disconnect or barriers to the implementation from an industrial perspective for additive when you get into multiple software packages and things like that. But not to kind of burst everybody's bubble, it still can cost less than other manufacturing methods. So as you are looking at design freedom within additive, some key aspects to consider are things like part lightweighting, as Ashley mentioned, topology optimization, part consolidation, things like that. So I'm not going to go over all these questions, but we do have these questions that we can provide to you later. And they're just simple questions of, how do you identify what kind of part is ideal for additive? And so these aren't the end-all, be-all questions for determining that, but they're pretty good starting points that if you can't answer some of these questions, or you answer some of these questions in a negative way, then that part probably isn't best suited for additive. So we can provide all of these questions to you at a later time as well. So jumping into kind of our last topic on consolidation, or sorry, not consolidation, but nesting of parts. That is a big piece, especially as you get into larger scale production of additive, that comes into play. So if you take things that, for example, such as angles, you take also into account kind of the design itself and cavities and holes. But overall, those don't have as much of a play in additive. They do have a play when you consider potentially wanting to create a packed, dense, part cake, as I'm typically call it, such as you see on the right-hand side here. So ways that you can actually get a much denser part cake is, considering draft angles. Yes, additive doesn't need draft angles from the standpoint of compared to injection mold tooling, things like that. That is a big drawback for injection molding, is draft angles, undercuts, things like that. But it does have its benefit in additive as well, such as stackability you see here. Another aspect for part density or part cake density is abstract designs. So a key benefit of additive is that you can do integrated hinges. You can do fully assembled pieces that then can fold after they're pulled out of a machine such as an HP machine. So those types of considerations, as you can see here, this folds out to be basically a box. And so if you were to print each of those boxes, you might be able to fit 4 or 5 on this in this image, whereas now we have, you know, a few dozen. And then overall, the communication between the software, machines, design, engineers, and the production application is key to pulling that off. You don't want to design something that's just printable and ultimately isn't going to have use for your end customer or your end product. So Ashley, I think you have a couple of comments on a couple of great application that you brought up here on that topic.
Yeah. I put this example together actually for the Antec conference, which is a big plastics conference I guess it was about a month and a half ago. But I thought it was worth showing here because this is the type of thing that you guys will get to see and do if you take up Saratech on their boot camp. So in this case, I've got this little plastic part. This came out of another assembly. I did not design this, but took it out of an assembly we had, and it's a little pneumatic raceway. There's 5 little tubes that go through these corners here, and it basically keeps the raceway from collapsing or kinking as the tubes go around this corner. So the first thing I did was I went through and redesigned this, and I basically stripped away a lot of the material that I didn't think was necessary to try and get a print that would be as efficient as possible for additive manufacturing. So that was sort of step number 1, and that was you know, the normal, typical, what you'd consider a redesign of a part for additive manufacturing. Now, what I thought about then after that is how can I make this part as packable as possible, specifically thinking about the HP printers in this case, to see how many of these I could possibly pack into a build volume. And so then that gave me the idea of having an A part and a B part. So what I did is I took this same design and I adjusted it just slightly to make a B part, where the radii for the corners is just offset. So there's still 5 tracks. It still has the same basic functionality as the A part, but the radii are different. And what that allowed me to do is take those 2 parts and pack them together like you see them here, closely nesting them. And now I have a small little assembly of those parts, and I can then replicate that assembly in my build tray over and over and over again and get a much tighter pack because they're made to nest together. So it's a small little design consideration, but again, something you want to do at design time with knowledge of the type of printing you're going to be doing, the machine you're going to be using, and the method you're going to use to print, taking that information and adjusting your design just slightly to make an A and a B version of a part that will pack much tighter into a build volume and give you much better efficiency than you would have with just a single part alone.
And I've got a couple examples of that as well, Ashley, here. I'm going to actually jump through it for time aspects. But basically, we have this part up on the left-hand side that is a cap. This was actually provided by our customer, Forecast 3D, who does a lot of this consideration as they own currently the largest install base for MJF technology and do a lot of production applications like this. So as you can see on the top, as it was designed, they could only fit 42 of these parts into an MJF build envelope or bucket. In the bottom, that part was redesigned, still has the same functionality, but redesigned with these little channels you see, and now they could fit 210. And you might think, okay, well, great. Well, how does that affect me? Well, ultimately, it does affect the cost that you incur from especially using a service bureau. You know, the more they can pack into a machine, the more material they can actually use and be more efficient in that process, the lower cost, you know, per part that you're going to actually probably see in production. So it isn't a straight line cost method that you commonly see advertised in the industry. And then here's just another quick example of that. So straight walls and then adding a draft. Still same functionality for that particular example, 75 parts versus 360 parts, and then the cost difference that also achieved for that example. So I just wanted to summarize a couple points on applicability of additive and where you want to potentially look at that. So this is a slide that I've used for quite some time now of applicability in aerospace, but it can really be used across a lot of different industries. And so a lot of people still see additive as just a primary use for prototyping, but then also want to try to get to full production. And as you can see here, at least in aerospace, it's commonly used and most widely benefited from in the manufacturing and assembly process. So tools, jigs, fixtures, assembly aids, those types of things, where you don't necessarily have the criticality of full production, but you can get a lot of the cost savings of using additive for tooling and things like that. And then my last slide is really where you start seeing the diminished opportunity or benefit for design for additive. Obviously, you can implement design for additive at any stage in a product's life cycle. But really, as you look at this, when you start with a part and are able to consider the entire life of that part and design to that entire life from a design for additive perspective, that's where you're going to definitely get the most unique value proposition out of the tools that Ashley mentioned, whereas you might not be able to change something because of the part that part meets up with or things like that as you get further along in the production life cycle. So Ashley, I think you have a couple ending comments as well.
Yeah, so I just wanted to go back and reiterate that additive manufacturing is a process, right? Depending on who you are, your company, you may be involved with the design side, you may be involved with the manufacturing side, but all of those various different pieces of this process need to work smoothly together if we're ever going to push additive beyond just prototyping and get to an industrial production type of process. And so we've talked about the things along the top here today, and we do have all of those integrated into our NX solution at Siemens, but it's also important not to forget the rest of the process as well, the prepping, the validation, the simulation, the post-processing, the validation, all those things you have to do to have a good, proper industrial additive manufacturing solution. And so again, we've worked really hard to make sure those things are present in our software, and we are certified for use with HP printers, and we've taken real care to make sure all these things work really nicely together, and hopefully you all will, like I said, take advantage of Saratech's offer here for the boot camp and get some real hands-on experience with how those things work.
Thank you, Ashley. And so just as a quick summary, we discussed some of the key considerations for design for additive. We discussed the Siemens tools and capabilities that allow that implement a lot of the design for additive characteristics that you saw, and then some specific examples of use of design for additive and those considerations in MJF or MultiJet fusion from an HP product perspective. And so just to kind of wrap things up, you heard Ashley talk a little bit about our additive manufacturing workshop, or boot camp as we're calling it. So I just wanted to touch base on why we offer that. So we have a complete design for additive curriculum that entails 6 days of design for additive perspectives. And the key point here is that, as you might see with a lot of other design for additive courses, they might focus just on the actual software piece, sorry, I shouldn't say software piece, but the actual CAD piece. And we feel that, as Ashley mentioned, with all the connectivity of the Siemens products, that there's a lot more to it. There's a lot more to how are you going to inspect this part? How are you going to prove viability for use in the application? Things like that. So we actually have a few things. One, we have a Design for Additive 101 kind of crash course that we offer. And then we have 5 days of training, only 2 of which actually focus on the CAD portion, or the actual design portion of design for additive manufacturing. The other portions factor in, okay, choosing the right technology, choosing the right material, things like that. What we're doing as kind of a special for next month is we're doing a 3-day design for additive boot camp. We're inviting you guys to participate. You will be able to have hands-on training with an instructor, one-on-one in most cases, of your own parts. and out of that, you will actually leave with that part redesigned and printed in an MJF or on an MJF machine. So we're offering this course July 24th and through 26th. It's a 3-day course at our facility in Mission Viejo / Laguna Hills area, which is Southern California. And we'd love to have you there. We normally charge $1,600 for this type of a course, but we are offering a few free seats. So if you are interested, please reach out to us. Please reach out to both the phone number and email, as you see listed there, info@saratech.com. And we'd love to share with you a lot more of the details of that course. And we would love to see you at that if you do have interest. So I just wanted to present Ashley's contact information and thank Ashley very much again for participating and helping us present on this topic. And so I think we're going to pass it back over to Monique for questions and answers.
Awesome. Thank you so much, David and Ashley. Excellent presentation today. We did get a great question in. John says, we are new to AM. Should we start with a new part from scratch or by redesigning an existing part? And how do we find a good candidate part to begin with?
So Ashley, you want to go ahead and take that?
Sure, yeah. Well, to be honest, we could probably do a whole webinar just on this subject, but the answer is that you can really do either. But I will say the one thing you don't want to do is take an existing part and just print it without any changes, right? Going down that road will absolutely lead to a part that's not optimized for additive manufacturing and will undoubtedly cost more than the original part. Finding a good candidate part is usually a multi-step process. You know, you kind of go through this thing where you figure out what hardware you're going to use, say it's an HP printer, and then you identify parts in your library that might physically fit within the build volume of that printer. But you want to also look at things like economics. Can you optimize the part to reduce the material usage? Can you fit enough of them in the print volume to make the economics work? And of course, if the part can't be manufactured any other way, then the economics change. But you'll still want to take that into consideration, and you'll want to take the geometry and run it through some validation routines like the ones we talked about to make sure that it's okay for printing and there aren't any areas that you might have to worry about. But those probably aren't all the steps you'll have to take, but it's at least a good start, finding things that fit, finding things that go through the validation routines.
Awesome, thank you.
And just to add that to that real quick, one of the things to consider is that your normal parts, if you start with a part that's already been designed, it was designed for some form of manufacturing, right? And so if you took, say, for example, a part that was designed for CNC and tried immediately adopting that for injection molding, you might have a part that comes out extremely expensive because you have, multiple slides and things like that. So, people on a regular basis are designing for manufacturing applications. And so we do see a lot of times where people are just trying to adopt a particular part that's already been designed for additive, in an additive process that hasn't been designed for additive, and typically they will see a negative result of the value.
Okay, and then we also had one more question. It says, it is obviously possible to create production parts with additive manufacturing, but is it something the average company should expect to achieve in the near term?
I guess I can take that one as well. So I think the companies, as we talk to people at various different events and engagements, one of the major hurdles that they face is access to the right set of resources that work together. There's the hardware side, the software side, but then there's also this sort of empirical knowledge, as people know-how side. And the hardware and the software are coming together pretty nicely, to be honest. I mean, things are evolving and moving at a fairly rapid pace to get those things in line. But it's the know-how, the empirical knowledge is the aspect that many companies are still missing. And companies who want to create production parts in the near term, you might be best served to contract with the service bureau at the outset. And then when you're ready, when you have some of that empirical knowledge, you can move the process in-house if desired. You have this process where you need to understand proper design, analysis, and the manufacturing processes around additive before you can really make the process sing. And the real value here comes when companies start to adjust you know, their design, their manufacturing, their business practices around additive, but that can only come after you've sort of gained that experience. And so as you saw in our presentation here, you know, we're creating additive production parts today at Siemens, but that capability came after painstaking research and knowledge acquisition about how additive works and the types of parts that are possible to produce. And we spent, frankly, a lot of money and time figuring all those things out. So as I stated earlier, we're trying to build some of that into our software as we learn it, but it's a process that's definitely something where you're going to have to, you know, acquire some knowledge and take the time to do that properly.
Awesome.
And I think to add to as well, Ashley, you know, that is obviously one of the main goals of our Design for Additive curriculum, is to try to jumpstart companies. I couldn't agree with Ashley more that it does take a lot of knowledge gain. There is a big knowledge gap there if you're just starting from scratch. We also, through our engineering services organization, can do customized training as well. So, you know, multiple weeks of training, multiple events where we can go in and sit side by side with your engineering staff to help them pick out the right parts and lend this knowledge that, you know, Ashley is mentioning, that we have, you know, over decades of experience within our team here at Saratech. But then the other key point that I wanted to touch on is a lot of people, when they hear, okay, let's you know, go for production, or you know, they have an initiative from a CEO level within their organization to implement additive for production. A lot of times they try going for that holy grail of, you know, the end use part printed right off the machine and used in their application, you know, for an end use part. And a lot of times that's where I see companies flounder. So I like to recommend that customers look into hybrid applications. And if you weren't able to participate in our webinar that we had a few weeks ago on hybrid applications using additive, you know, that might be something like combining composites with an additive honeycomb core to create a very unique part, but ultimately not rely on just the additive portion for production, right? And that means, okay, you got to look into what you need to adopt to be able to implement that product in a production environment within aerospace or something like that. Well, if you take some of these hybrid applications, there's already certifications for some of these types of honeycomb inner structures, or investment casting using additive as the lost wax method, you know, things like that you can jumpstart that certification process for many different industries. And so I advise typically companies don't just go for that end use part to start with, for a lot of the reasons that Ashley mentioned as well.
Excellent. Thank you, David. And we actually did get one more question in from Luis. He asked, looking to get into metal additive manufacturing, do you think now is a good time with new technology coming out so quickly, or will it be outdated in a couple years for production?
So one of the things that I've seen in especially metals is, yes, there are new capabilities coming out on a very rapid pace. But if you look at, say, for example, powder bed fusion, a lot of the powder bed fusion systems have been improving and adopting, or I should say retrofitting systems to allow for upgrades, because they know, okay, if we tell customers to adopt this for production now, you know, if we just come out with something that's not upgradable, then they're gonna you know, lose that focus on production down the road. So definitely is something to consider now, especially with a lot of the new capabilities that are out. It's starting to enable production a lot better. So, you know, things like the post-process technologies for support removals and the software generation for you know, support creation and things like that in metals. And then as you look at new technologies, we can also help advise if it's potentially something you should wait on, depending on what your application is. So there are some new technologies coming out that are utilizing more of the metal injection molding, you know, techniques. So that has benefits, but it also has drawbacks. So yes, there are new technologies, but there's a wide array, of metals technologies that can suit your production needs today.
Awesome.
Ashley, I don't know if you have any other thoughts.
I guess I was just going to say, don't underestimate the amount of learning that you get by doing as well. So when you consider buying a machine, it's not just the parts you're going to get out of it that are part of the value that you get from that. Part of the value is this empirical knowledge we've been talking about how the process works, what kind of parts you have in your particular business that might be applicable to additive, and that's sort of it's unquantifiable, unfortunately, but it's also very, very valuable. So we see a lot of customers who kind of dip their toe in the water by buying one of these very expensive machines, and then, like you said, they change a lot, and everybody's concerned about that, right? Am I making an investment that's going to be good for a while? But the companies that do make the investment that we see often tend to, not very long after, be investing in a second machine and a third machine, because they find applications for additive that they never would have considered had they not had a printer in-house and the ability to try things. So it's one of those things where it's hard to quantify at the beginning, but I think you'll find in a lot of cases that you're able to make the value proposition much easier once it's in your hands than it is before that point.
All right, excellent. Thank you so much, gentlemen. That's all the time we have today for questions and answers, but if you should think of anything, please go ahead and email us at info@saratech.com, and we'll be happy to get you in touch with an expert. And thank you again, everyone, for attending. We will be posting this video to YouTube later today. Feel free to pass along to your friends and colleagues, and be sure to subscribe to our channel. Follow us on Twitter and LinkedIn for upcoming webinar dates and topics. And don't forget to stick around for about 10 to 15 seconds after this webcast ends to fill out our survey. Let us know how we did, what you liked. We really appreciate your feedback. And thank you again for attending. Have a great day.
Thank you, everybody. Bye-bye.